record from now on, so I'm really sorry for that. I'm recording from now on. That's my fault. Apologies for that. I should have spotted that. So I'm recording now. The slides will be available and the lecture will be available from this point. So apologies if you're watching the recording. I didn't record the previous. I made a mistake and didn't record the previous slides. Apologies for that. I may be able to find a previous recording of this lecture, in which case I would put it up. Sorry about that. Okay. Some people try and do deep halos. So again, if you're latency dominated, you say, well, it's actually better to send a small number of large messages. And what you can do, I don't want to go into the details, but you can send halos of depth 2. You can send more data than you need to, and then that allows you to do. You send 2 halos every second iteration rather than 1 halo every iteration. The logic for that becomes very difficult, and it may not be obvious, but it's often comes with its downsides. I don't want to go into the details of it, but in a real program, it also means you need to do that. If you think about it, for naive halo swapping here with an up, down, left, right stencil, you need to communicate data with your 4 neighbors. If you do double depth halos, you need to communicate with 8 neighbors. You need diagonal communication. So it comes with its pros and its cons. I mean, again, it's the logic's quite hard to get right. It can. So I'm not going into any detail. I have some nice pictures here. But I would say, you swap depth D every. So this is showing you swapping halos of depth 2 every 2 iterations. Then you do. The problem is you need this diagonal communication, because if you do up, down, left, right twice, up, down, left, right followed by up, down, left, right gives you a diagonal. So you need diagonal information, which is a bit of a nightmare. So you end up doing more communications. It's not a panacea. So I'm skipping over a bit here, but I would just say, again, people often say I will do deep halos, but that's not always not always the case. Not always beneficial. You need diagonal communications. And it's even worse in 3 dimensions. You go from 6 communications to 26. Now, there's ways to mitigate that, but it swings and roundabouts. So I'm almost finished. Persistent communication is very, very like non-blocking. The standard method is you would do I receive proc up, I receive proc down, I send proc down, I send proc up, and store these in requests, and then do await all on these requests. The persistent communication, you set them up once right at the start of your program. You say, I'm going to want to do this communication, this one, and this one, and these requests now are persistent. What I mean is that you do start all. So this ties this request is then tied to this call. It encodes all the parameters, including the buffers, everything. Okay, so start all says this is only possible if you call the sends and the receives every time with the same parameters. Okay, with the same counts, pointers, everything. But that's often the case. And then every iteration, you do MPI start all and MPI wait all. Unfortunately, message ordering, so this gives MPI a lot of freedom, because you're saying, I want to start all these 4 requests, and that allows MPI to start them in any order. And so message ordering isn't guaranteed. So you may need tags to correctly match the messages, which is a bit ugly. In practice, this doesn't have a huge number of benefits, because actually there's very little overhead. I mean, the MPI developers have been very good, and there's very little overhead in calling an MPI. This saves the overhead of argument checking and processing the arguments of the calls, because you do it once and stash them away. But actually, in practice, that's a low overhead. But I wanted to show this because it's a relatively elegant way of programming. But secondly, there are now going to be persistent collectives, and it will be the same. It will be the same syntax for persistent collectives. You would say, I want to do MPI all reduce init, and then you do MPI start all on that. So and it's also illustrated in the example. Neighborhood collectives. Standard collectives are applied to a whole communicator, and all gathered collects data from all P processes. In an all gather, every process gathers from all the other processes. A neighborhood collective is the same conceptually, but it only applies to the neighboring process. So MPI neighbor all gather only collects from your neighbors. What do your neighbors mean? Well, neighbors means I'm seeing a few messages popping up, but I'm not. Okay, fine. I'm seeing some. Okay, sorry. I thought I had some outstanding chat messages, but I don't. It was an artifact of the interface. So MPI neighbor, spelled in the American way. Oops, sorry. MPI neighbor all to all collects data from your neighbors. What do your neighbors mean? Well, it requires the communicator has been constructed with a topology. So I cover this in the basic course. MPI can't create. If you do an MPI neighbor all gather from MPI can't create, it allows you to gather from your 6 nearest neighbors up, down, left, right, forward, backward. If you have a more general arbitrary communications pattern where any process communicate with any other one in a graph, you can use a graph topology. I don't have that, but there are various MPI graph create routines. Each process can be connected to an arbitrary number of neighbors. But I think the philosophy is quite straightforward, and it's illustrated in my example code for this. So, used for halo swapping, MPI neighbor all-to-all implements halo swapping. Send and receive data with all your neighbors. And so in the halo bench exercise, there's a 3D Cartesian grid. And the MPI library can implement these in any way it chooses, hopefully efficiently. In fact, it probably just does non-blocking sends and receives and await all like you would, but the code is much more elegant and compact, and it does at least give the MPI library the option of implementing it effectively, optimally, because you've said MPI neighbor all to all is a single call which implements halo swapping. I have a lot of these diagrams for collective communications, but they're really just the same as the main one is saying that if processes enter a collective at different times, then there will be a delay. So if you've got a broadcast and the route is late, all other tasks have to wait. A reduction, if you've got a reduced and the other processes aren't ready, it will take time. But to be honest, the real ones where you get this are ones which synchronize, like all to all. Often you do all to alls if you're doing Fourier methods, matrix transposes. And so the main one is all reduce. And if you do an all reduce, it imposes a synchronization. If they enter it at different times, you will get an overhead. And the classic reason for that is that you have load imbalance. So instead, collectives are hopefully optimized for the architecture. They're expensive and they force synchronization. So if you find your program spending a lot of time in all reduce, which is often, first is make sure that you have load balance. Second, do you need it? Yeah. I mean, in many iterative methods, reduction use operators are often required to check for convergence. But maybe it'd be quicker to only check every 10 iterations. Okay, maybe beneficial to reduce the frequency of doing this compared to sequential algorithms. Sometimes, often people do all reduces for diagnostics. They compute a diagnostic just to print it out. That could be very expensive. So I would really the key thing to minimizing the time spent in all reduce is really to minimize the number of times you call it. That is often an algorithmic decision, or just saying, look, I'll only print out debug information every 100 iterations, not every iteration. That you might say, well, surely non-blocking collectives sort this out. I am dubious about that, and it sounds like the solution to all your Rails non-blocking collectives, but actually in practice they may not be that useful. I'm not that mad on them, but you can try them. So it's an I all reduce and a wait. So the idea is that you can overlap the cost of the all reduce and the synchronization overheads with computation. Does that really happen? I doubt it. So summary, we've talked about lack of parallelism, load imbalance. We've really talked about synchronization and communication. And the bottom line really is obviously to minimize these things, but when you're doing point-to-point communication and halo swapping is the classic example. Do not assume any ordering. Issue as many non-blocking communications as you can, and then and then wait on them all at once, which allows the MPI library to deal with them in the order that they happen, which can vary iteration to iteration, rather than the order in which you think they're going to happen, which you may not be able to predict. So the exercise for this is really to run a halo swapping example, which is here. I've distributed this just as a, it's just on a GitHub page. So the description is a bit brief. It's in the README. Basically, what the benchmark does is it sets up a 3D array of processes using a Cartesian communicator and swaps halo data up and down in all three directions. And it does 1, 2, 3, 4, 5, 6, 7, 8 methods. It does pairwise swap in each direction using send, receive up, down, left, right, forward, backwards. It does another technique to break the deadlock, which I've seen people use, where you split the process. So the problem is, if you just use blocking communications, you run into the problem of deadlock. Because if you issue the send first, there's no receive. If you issue the receive first, there's no send. MPI send receive breaks. The other way to break the deadlock is by hand, to split the processes into odd and even groups, and have the odd processes send first and receive second, and the even processes. I've tried that. I've used non-blocking with pairwise in each dimension in turn, with I send and receive, or the other way, I receive and send. Pairwise swapping each dimension in turn using I receive, I send, and wait on them both. And then I do the full shebang, non-blocking communications in all dimensions and directions at once using I receive and I send. And then this is what I would recommend, and hopefully we'll see this as the quickest. And then do 12 waitors. It's 12 because you have 6 neighbors and you have a send and a receive in each neighbor, for each neighbor. So you have 12 requests. I've implemented it with persistent and neighborhood. Note the bug. The neighborhood collector may fail the consistent test as one upload due to an unfortunate bug in some of the implementations. This has been fixed now, but that was a problem. Unfortunately, that shows how rarely these oh, sorry, my share didn't work. I'm really sorry. Sometimes the share application screen is not working. So I will go back to that again. Is that working now? No, it's still not working. Sorry, the sharing here is not being very good. There we go. Sorry, I was reading through this. So I've gone through these are the methods. So I linked this. This is linked in from the exercise main page. Description is in the README. Okay, so I was seeing something different from you guys. There's slightly. I wasn't seeing it being shared, but that might have been a local issue. And then, so hopefully you should be able to git clone this, and then go into the directory and just submit with ARCHER2 So this really is just the exercise here, and we'll look at the results and discuss them. Oh, okay. When I say wait all times 12, that's slightly. What I mean is a single wait all with a count equals 12. Yes, okay. I mean a single wait all with count equals 12. I will fix that. You're right. That terminology is slightly confusing. I will fix that. So thank you, Lee. I will fix that right now. I realize that's slightly. Yes, so I'm assuming the Cray compiler, just because, for simplicity. This code is written in Fortran, but hopefully it should be sight readable to C programmers. I will fix that issue you've just spotted. No? let's hope I reload. Yes, so I fixed that. That was a good point. Thank you very much. That was, and I will also, I think the other exercise you could do, I've just told you to run it, but actually it would be interesting. I've picked a particular halo size of something like 10K doubles, I think. It'd be interesting to try much smaller and much larger versions. I'll put a comment in here to illustrate that. But hopefully just try and run the code out of the box. I'm going to take a 2-minute break back into. So I've just added another exercise here to think once, change the buffer size to be very small, a few tens of bytes very large, see if that affects the results, run on different numbers of nodes. But as I say, there's some tweaking required. It's a very simple code, and you'll need to. There's a variable which controls the number of iterations, which you'll need to vary because and if I show you that, I can show you it in the code, which is, where is it? There's the. You'll see at the top, nbuff is 10,000, which is the number of doubles, and nrep is the number of repetitions. You'll need to change those to balance out. So has anyone just managed to compile? Okay. So what I'll do is I'll wait maybe until about 20 past, and then at 20 past I'll go through the results just to see if they make sense. So what do you mean, Daniel? MPI demonstrates doing a lot of work here. What do you mean by that? Just so what MPI demonstrates is just a helper routine, which tries to it will try and get a balanced decomposition. So it tries to basically factor. What's the default number of processes? How does it? Let's have a look. It runs on. It's default size. It runs 16 by 8 by 8. So it tries to. So the cube isn't obviously right, but in general, you would guess that you want it to be. That would be your first guess, because why is that your first guess? Because it gives you in general, it would give you minimal surface to volume, minimal communications volume. If your domain, the thing is, MPI demonstrate doesn't know how big your problem is. But if your problem is L by L by L in a 3D grid, you probably want the domain decomposition to be something like P by P by P near a cube, because that minimum. If you have very long and thin domains, you get a high surface to volume. Yes, so you're right. that's okay, fine. So yes, so that my argument there is the theoretical argument, which what am I trying to say? Which what am I trying to say here? Is a theoretical argument based on assuming it's bandwidth dominated. In reality, you're right. You may be, if you're latency dominated, if you have small messages, you would want to have the minimal number of neighbors. So you are allowed to give MPI-DIM to create. You could tell MPI-DIM to create. There is the option to tell it the first dimension has to be 1. So you could do pencils by saying the first 2 dimensions have to be 1, and then it does it into, well, pencils would be the first dimension has to be 1, slices would be the first 2 dimensions have to be 1. The problem is that my code assumes you need to do halo swaps in every dimension, so it would still do sends and receives to itself. So it wouldn't be optimal for that. You could code, but yes, you're absolutely right. In general, it's not obvious that cube is right. It is for very large problems where you're bandwidth dominated, but if you're latency dominated, then you're right. You want to have lower dimensional decompositions. That's a good point. And again, I mean, for small problems, then that's a good argument. Yeah, you're absolutely right. So so MPI-DIMs create yes and no. No, MPI-DIMs create just gives the says I want it to be a 60 byte. MPI cart create has that option. So MPI cart, what I'll do is easier if I actually show you the code here. And I've lost my browser because if you look at the Halo bench, is that legible? Is that reasonably? I'm going to make it a bit bigger. So yes. So as Matthew says, the reorder is an MPI can't create. But if you look here, I have reorder equals false. I think reorder equals false. So I have not allowed it to do that. Now, if you did reorder equals true, it would be able to do that. However, so yes. However, the it's worth looking at that. Actually, it'd be interesting to try that. However, I doubt it does any good because the default ordering, which is linear, the first 128 processes to the first node, the second tends to work well in. Why don't I let's try that? Okay, so I will try that. Hopefully my code is still correct. I've never tried it. It's possible that it isn't correct, but because I've never run it. You know, I may have messed up the logic. It's possible that I haven't. What am I trying to say? If you have reorder equals true, then your rank in cart com is not the same as your rank in com world. Now, so you have to be careful to distinguish between the two ranks. And it's not. I'm not 100% convinced I've done that because I've never. I should have, but I'm not guaranteeing it. So my code isn't running at the moment, but I'll have to wait. Okay, that's running. It will, if I've got the logic wrong, it should fail the internal consistency test because that's based on, I would need to print out the physical locations of these processes to know. So that reorder equals true may have made no difference at all. But I'm seeing very little difference, if any. It could be it's not a big enough problem. It could be it's within noise. Well, actually, I think it's probably within. It seems to be. Actually, it's interesting. I don't know if that's reproducible. Yeah, a few percent. I don't think it's significant. It'd be nice if it were, but I don't think it's significant. So I will, if it's okay, I'll just sort of wrap up the exercise by going through some of the results, the results. Yeah. So I'll go through the code first, just to show you how it works. So there's a bit of a driver routine, and it does some checking. I check the data, but basically all the meat is in Halo swap.f90. So so there's some COM data here. So Halo send receive. Okay, if you look here, I loop over. Everything's done a number of repetitions times. Okay, but I loop over the dimensions, then the directions, and I call a send receive, which is end. The problem with deadlock is that if you issue a send first, you never get to the receive. If you issue a receive first, you never get to the send. MPI send receive is a way of issuing the send and the receive at the same time. I don't recommend using it. I think you should use non-blocking communications. They're much more general, much more useful, but some people use send receive, so I thought I'd benchmark it. Halo red black basically splits the processes into odd and even groups, whether your coordinates are, some of your coordinates are even or odd, and basically I loop over the repetitions that I mentioned, the directions, and half of them send first, then receive, and the other half receive first, then send. So I've seen people do this as well. Again, it's not very elegant because you're imposing and ordering, the code's complicated, but I thought I'd put it in there. Halo's I send receive wait is the pairwise thing, but not done with send receive, but done with an I send and I receive, still pairwise. Okay, so I only have one non-blocking communication, an I send, a receive, and a wait. The other one is the other way around, just for the fun of it. You have an I receive, an I send, and a wait. Again, looping sequentially over the dimensions. So dimensions is 3, directions is 2, up, down, or down, up. I can't remember which way around it is. Halo I receive, I send, wait pair does 2 non-blockings, but still does them sequentially over dimensions and directions. So this is n request is only 2 here. I send, I receive, wait all. Okay, slightly okay. This is slightly longer code, but basically it loops over the I request is 1 to n request is send or receive. That's why that's send and receive. Their dimensions, so that's factor of 2, factor of 3 is 6. That's 12 of them, and then I do, if it's a receive request, which is the first time through, hopefully it issues all the receives first. This is just trying to make the logic quicker. On the second time through, it issues all. So I think this issues all the receives first, because receive request should be 1. Hopefully that's true. And then it does the MPI wait all, endure times the request. So this is what I would recommend as the general halo swapping routine. But just to show you, this is the persistent stuff. This logic is almost identical to this logic here, okay? But what I do is, rather than issuing these every time within the repetitions loop, which is of order thousands, I do a single setup, okay? So I initialize them. So the logic is almost there, but and I have to use tags because, as I said, it's a slight technicality, but persistent operations don't maintain message ordering. The idea is that MPI should be allowed to start them in any order it wants. You need to have a different send and need to tag these. But I do MPI receive init, MPI send init. It's almost the same as the previous code. And the actual thing is basically, for MPI, start all of them and wait for all of them. So that you may not see the syntax before. It's actually relatively elegant. And then I have to release these persistent handles. Yes, because have I allocated them somewhere? Oh no, because I've finished with them. I have to release them. Sorry. So that's okay. These are persistent, so I need to release them. Sorry, I wouldn't normally have to release a handle because it. Sorry. Okay, I'm scrolling about too quickly here. Fine. I have to release them so they're available. It's not a memory leak. Sorry. And then this all to all. Okay. You'll see it's really quite. Yeah. So actually, Kevin's made a very good point here. That there are two ways to reorder your processes. One is to use MPI can't create with reorder equals 1, but actually you can do it externally. So that is start with the default decomposition. Start with the default assignment of processes to cores, and then change it, or at least logically renumber in your program. But what Kevin's suggesting here, which is probably as equally good, is to change the default order. So when you launch the program, say, I want process 3 to be on node 5, rank 7, and that's quite long-winded, but there's a grid order utility which basically generates these things. And for I think it has 2 options. For regular grids, it will give you what it believes to be the optimal placement. But I think, I might be wrong here, but I think it can even look at a trace file. It can look at a runtime trace file and look at the communications load and suggest a reordering. Or at least there is a way of doing that within CRAPAT. But what I wanted to show you here about the neighbor all-to-all is this says, you see how this is halo swapping. Okay, now it's simple because I'm using contiguous buffers, send buffer and receive buffer. I'm not trying to pick out halos from a 3D array, but you can do that with some work, which I will cover in the next lecture, actually. But yeah, hopefully you can see that this syntax is really quite elegant compared to this stuff here, I think. So I quite like, so how does the performance work? It's what we really care about. And I will now share my so this is the one which was, I ran on a slightly bigger grid than you might if I used the biggest. We have 16 nodes in our reservation. We still had like a run on the reservation. So each halo has 10,000 doubles. That's 80 kilobytes, and so that's about half a megabyte per process. And so let's have a look. I don't know if I can get them all on one screen. But send, receive, let's look at the bandwidth. 11 seconds, that's not very good. Surprisingly, red black is quicker than send, receive. I don't understand why, but there you go. These ones I send, I receive, wait. They're all anything pairwise is down at 11 seconds, but the I receive, I send, wait all is 8.5. Now I would expect that these differences would grow. We're only on a few thousand cores. I would expect these differences would become more noticeable as we went to larger problem sizes. But you can see there is a significant difference. That send receive, which what people often do, is quite bad, 11 seconds. Red black surprisingly good, 9.5. They're almost 11 for these guys, but the one I recommended is 8.5. That's the best. And persistent start wait all is about there. It's at 8.8. It's not bad. And neighborhood is almost exactly the same as this. I suspect if you looked, well, I'll come back to that. If you looked at the neighborhood collective code, it would just be this code. And so Jervis, the wait all versus point, why is that? It's because it's tolerant to the. You're saying the other ones. You're saying I'm going to send up and receive from down, okay? But you're waiting for the receive from down. Maybe the receive from the left is ready, or the right, or the other one, okay? You're imposing an unnatural order. The wait all issues all the sends and receives at once and says wait for them all. So MPI is able to say, oh, there's a message coming in from up the way, I'll receive that. So you will process the messages in the order they come in, rather than if you prescribe the order, I want to receive from up, maybe that message isn't ready and you end up waiting when you could have received the one from the left. Does that make sense, Jovi? It's saying that issue all of them and let them. So send, receive, and neighbor all to all. So neighbor all to all, send, receive is imposing an ordering. So send, receive is saying, oh, you don't. I'll have to share a different screen. I didn't mean to do that. Send, receive is basically saying, where are we? Halo send, receive. It's doing the bad thing. It's saying I'm going to send up and receive down. So this sends one message and receives one message. Okay. So I have to repeat it for every dimension in every direction. So I have to call it 6 times. Send, receive, up, down, blah 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 blah. Yeah. All to all is very much more like the neighbor all to all is saying do at the same time. So it achieves the same thing, but I only have to call it once because implicitly it is doing everything at once. It's saying do a halo swap. I've lost it here. Do a halo swap in every direction with everybody all at once. And so that is basically the same as the non-blocking code. But send, receive is mandating do the up first, the down, then the left, then the right, then the forward, then the backward in that order. And that's not a good idea because that may not be the order that they're happening in real life. Whereas this is saying do them all at once, which is logic, which is conceptually the same as the completely non-blocking. I think if we could find the code for this, it would do nothing, but it would just be this code here. Okay. Okay, so we're bang on time. Okay. Well, you're saying I use send items to then wait. What do you mean by wait? As opposed to wait, or because you need to do multiple waits. So what do you mean by wait? Do you mean it would be bad to do? That's bad because you're saying, is that bad? Probably not, because you're saying wait until the first one. It'd be worth. I mean, you should still use wait all because the more freedom you give MPI, the faster it can be. So wait all is best because MPI has all the information at once. Multiple wait, probably not. So if the first, well, Kevin, exactly. So I was saying it reimposes the order, but the point is, if the first wait is for the slowest one, you'll wait a long time, but then all the other ones will be immediate. So you're right. It's exactly my answer was exactly what Kevin said. Was going to be what Kevin said, that it reimposed the order, which is a bad thing. But you might be lucky here that actually the code is so simple that if you wait for the slowest one, then the other, I'll be interested. I should maybe put that one in. It will all depend on message size as well. The messages are large. Yeah, I don't know if anyone's had a chance to different message sizes, but I mean, it will all depend on. So this is but I'm quite pleased that the exercise does demonstrate what I believe to be the case, is that you should learn to use non-blocking communication and you should do as much non-blocking as possible. And in practice, you can often issue the receives very early, because you can issue the receives. It's often possible to issue the receives and sends quite early on. It depends on the logic of your program. So what we'll do now, I do apologize for any party recording that lecture, but I do like to stop and start the recordings, otherwise you get a single recording of sort of 10